Hey there, it's me, I'm back. Now we had just left off here finding the null and alternative hypotheses for this mean of the differences for our matched pairs. And I wanted to make a note to you all right here that if we had set up in the problem that it was after minus before, but if we had done that backwards, if we had done before minus after, then your alternative wouldn't have been a less than, your alternative would have been a greater than, right? Because if you're going the other direction, right, you expect after to be smaller than before, so you expect this difference to be greater than 0. So just keep in mind that it kind of depends on which way you're going, after minus before or before minus after. A lot of the times we're going to try to set it up for you in the problem so you can know which way, but if we don't set it up in the problem anywhere, then you just pick a way, right, because both ways will technically work. All right, so now what results do we expect to see from the hypothesis test based on the box plot of the before and after pain levels? So, reading box plots. You did this in chapter 3, remember? It was a long time ago. So you expect that it's going to show that there is a significant decrease, and you can see why here. I drew a little arrow here. Look, this middle bar of that gray box, that's the median, right? So the median for after, that means 50% of the after data is below, look, the minimum of before, right? So 50% of the people have moved down and are below what the lowest value was for pain before. Low, right? Okay, so let me write that up. Hold on one sec. There we go. All right, so now look at the following normal probability plot of the differences. Is conducting a hypothesis test on these data possible? Explain. Well, remember, to conduct a hypothesis test, let me go back here a minute, you have to have simple random sampling, which we have, sample or matched pairs, which we have, and then the differences are either normally distributed or your sample size is large. Well, we don't have a large sample size, so we need to know that it's normally distributed, and that's why we need this graph down here. So here is fine because all those dots are in there, so that means that it's normally distributed. So let me type that up. There we go. I just typed up what I just said, which is that even though we have a small sample size, less than 30, the graph at left shows that the data are normally distributed, so we're fine for doing a hypothesis test. Actually, we're fine for any doing inferential statistics, confidence intervals, stuff like that. All right, so now we're going to actually run the hypothesis test. So let me figure this out. Step 1. Oopsie. Step number 1. We are going to need to create some hypotheses. But we already did that. Let me go grab them. They're right here. So there are hypotheses. I'm going to unbox those, but other than that, we're good. Step number 2 is we're going to need an alpha level. But that's not too bad. We've got that as well. Because it's given to us in the problem that alpha is equal to 0.05. All right, so that's done. Step number 3, all right, here's where the fun begins. We need that formula. So let me go grab it real quick. There we go. There's the test statistic formula from just a couple pages ago with the hypothesis test all written out. Now, we already figured out this value. It was negative 1.923. We'd ran one variable statistics on it. And we already figured out this value is 1.605. More or less. I mean, technically I should do squiggly equals here because these aren't quite exact. We're rounding, of course, because these are continuous variables. Square root of 13, they're not variables, sorry, continuous values. All right, over the square root of 13. Now, you could try to type all of this into Excel, computer, whatever. However, it's easier if you just make the calculator find all of it, right? Because a lot of times people won't type this correctly. So let's figure that out, shall we? So if I grab the calculator and I think, okay, I want us to do stat and I want to go to tests. Now, which test do I choose? Aha, well, remember that I told you which test to use up in the little gray box at the top of the hypothesis testing sheet right here. You're running a t-test right there. So that's what you're going to choose, t-test. All right, so let's go back to the calculator. There's number 2, t-test. So I'm going to choose that. And then you have to choose data or stats, which we had data in this particular problem, so I'm going to stick with data. Our mu0 is our null hypothesis value, which, let's go back to our null hypothesis. Oops, I went too far. There it is. It's 0. See, mu d is equal to 0. So I'm going to leave that as 0. My data is not in L1, it's in L3, are not in L1, they are in L3. So I'm going to choose L3. My frequency list I'm just going to leave at 1 always. And then I'm doing left-tailed, right-tailed, or two-tailed. Well, we're doing a left-tailed test, which is in the middle. That's why we set up that alternative hypothesis. I'm going to go down to Calculate and press Enter. And there it runs the test for me, and it tells me that the test statistic is negative 4.319. So let me go back and type that up. So this is squiggly equals negative 4.319. Beautiful. Step 3 is done. Step number 4. Okay, well, that's where we draw a curve that looks like what it did on the other page, right? Oh, I forgot. Are we doing classical or p-value? I think we're doing p-value. So we're going to draw this picture right here, this p-value picture. Something with that, with the t0 at the bottom and the p-value labeled, all that good stuff. All right, so I copied and pasted it. Now let's get in here. So I got to open this up in a program because we got to label both parts. You got to label where that line is, and you got to label your p-value right here. Well, the labeling of the line, we know it's negative 4.319. It's what we just found above. And then the p-value comes from the calculator as well. It's right here. It's 4.986. Now, wait a second. This is a p-value. P-value is probability. It's the probability that you're off in this tail. Now remember, the entire curve, the area under the whole thing, is 1, right? So there's no way that there's a p-value that's 4.986. Is the calculator messing up? No, because if you look over to the right, you can see it's got e negative 4, which means scientific notation. This is 0.000496, right? You move the decimal 4 spots to the left. Okay, so the p-value is... I gotta click in there. There it is. So it's p-value equals 0.0005 because 4986 would round up that much. I'm going to shrink this down in size just a little bit. And there we go. There's our p-value. Okay, then we also need to get this number down here labeled. So let me open up the program. I'll be right back. There we go. I got it labeled. So it's negative 4.319. That's that vertical bar right there. And then the p-value is the area, which is 0.0005. All right, so step 4 is now done. Now step 5. We have to make a decision here. Now remember, we decide based on, if it's the p-value, based on whether that p-value is low. So we are going to reject H0. And here's why. Because the p-value, which is equal to 0.0005, is less than your alpha, which was 0.05. I think it was. Yep, it was. So since you have a low p-value, low probability of happening, you're going to reject the null hypothesis. So there is enough evidence to support the claim that Reiki touch therapy lowers pain levels. Right? Which shouldn't come as any great shock to us because when we looked at the box plot, it looked like the after was way below the before. Look at the table. I mean, so many values on that table were negative. That was kind of a sign that we were doing something right, right? We were lowering the pain levels right here, right? It wasn't half positive, half negative all over the place. It was mostly negative and some zeros. That's kind of showing that there's an effect, and we just proved, more or less, that there is an effect. Now, are we 100% sure that there's an effect? No. We're 95% sure because our alpha was 0.05. All right, so now we're going to repeat steps 4 and 5 using the classical method. So let me go grab that picture. So the picture for a classical method looks very similar to a, oops, that was a T0 value, not a Z0 value. I'll have to go fix that. So we're doing a left-tailed test, so we're doing this picture right here. So let me bring this down. There it is. Oh, and then oh, I just made a total mess of this. This is T0 because this was a t-test, not Z0. My fault. So let me make that T0. I'm working in a program that you don't have access to, so don't worry about that. And then I grabbed the wrong picture. All right, hold on one second. All right, there we go. I've got the picture drawn. So I'm going to label this. This was a left-tailed test, so I'm going to label that with all of alpha, because only one tail, so that gets the whole alpha. And then I need to find T sub alpha. So T sub alpha you can get from a couple things. You can get from the T table, which is, let's see, should be in here somewhere. There it is. So we need our degrees of freedom, which was 12 on this particular problem. And then our 0.05 was our column. So that would be 1.782, right? Negative because we're doing a left-tailed test. So you can get it from the table, or you can get it from your calculator. Hold on. Negative 1.782. There we go. If you have a calculator, if it's an 84, then you can do second distributions, which is above your variables button, number 4, which is inverse t, and say 0.05. My degrees of freedom was, remember that's n minus 1, so I had 13 patients, so 13 take away 1, that's 12. Oh, it's probably not going to take that. I'm going to have to type it as 12, sorry. So 12, and then I go down to paste. Enter. And there it is, just like the table said, negative 1.782. Okay. All right, so then we would still reject, but for a different reason now. So, oops, I better label this. So this is number 4, step number 4, that we're doing right here. And then step number 5 would be rejection still. Reject H naught. And this time, why are we rejecting? Well, you reject because your test statistic, which is negative 4.319, step 3 right there, is lower than your T alpha. Because T0, which was negative 4.319, is less than negative T alpha, which was negative 1.782. There we go. Right? In other words, you're in the critical region. That's what this is called. So 1.782 is called the critical value. Being off in this little dark tail is called being in the critical region. So you're off in the zone of, no, you're too far. I must reject the null hypothesis. And just another little side note, the p-value method's much simpler, and it comes from a calculator. So if you reject up here with the p-value, then of course you're going to reject down here with the classical method. If you reject with one way, you're going to reject with the other way. So check yourself with the p-value method, because the p-value method comes right out of the calculator. Go stat, tests, number 2, fix all this stuff, which we already did, and go down to calculate. And you can see with a p-value that's that low, 0.00049866, you're going to be rejecting your null hypothesis. Right? And so that this way is a way to back yourself up. The classical way is a little bit harder than the p-value way. The p-value way is the simpler method. The classical is what people had to do back in the day before they had computers and calculators. Just on a real quick side note, I want to take you to StatCrunch and show you how to do all this with StatCrunch real quick, because it's super simple. So what I'm going to do is I'm going to type up my data. So this is before, this is after. This will be, actually I don't care about that. Okay, so let me type these in. This was 6 to... All right, hold on. I'm going to pause you and I'll be right back. There we go. So I got them in before and after. You go to Stat, T Statistics, Paired. Click on Paired. You have Sample 1 in column. Now we're going to do after minus before. So choose Sample 1 to be after, Sample 2 to be before. Okay, just you can see down here that's the way they run it, mu1 minus mu2. So, and if you want to save the differences, you can, which we would want to say. And then we were testing against 0, but we want a less than 0 for our hypothesis. All right, and they're doing a different way. They're saying mu1 minus mu2. I don't really like that because it's not detecting that it's paired, but there we go. And then say compute. And look, 0.005 is your p-value. Your test statistic is negative 4.319, just like we said. The degrees of freedom is 12, just like that. Done. Simple as that.